Okay guys, in this video we're going to take a look at the sum of a geometric series. And so let's go ahead and refresh our memories here. When we talk about a series, this is the sum of the terms of a sequence. Okay, so a series is just when we take these terms of our sequence like A1, A2, A3, all the way out to AN here, and we add these together. This is what we refer to as a series. So we're going to be looking specifically at the sum of the first n terms of a geometric sequence. And know this, because it's geometric, like arithmetic things, they're very well behaved. So for what it's worth, to find these sums of geometric series, we're going to have a nice rule that's carved in stone that we can always use to go find these sums. So one thing I want to make sure that we do right up at the top of this here is that it says sums of geometric series here. I want to make sure that we put a little caret here. Sums of finite geometric series. Okay, so one thing we don't do with arithmetic series is look at, what happens not when you add up, say, a set number, but like all of these terms right here. If you were to add up the entire infinitely many of these, what would you get? It would actually add up to be like infinity. So we don't talk about infinite arithmetic sums, but we do talk about finite arithmetic sums where we add up just a set number of terms. Just because infinite wouldn't make any sense. Well, I got to tell you, with geometric series, we have both finite and actually infinite geometric series. So we're going to look first of all at our finite geometric series, and we're going to define it thusly. If for a geometric sequence we have the terms A1, A2, A3 all the way out to AN here, if we wanted to add up the first n of these, we would write it as the sum or sigma from 1 to n, so from the first term out to the nth term, of AI, where AI is our rule that gives us the term values for each of these successive terms. Remember that with arithmetic things, because they're so well behaved, because they're special in terms of sequences, we wrote S sub n to denote the sum of the first n terms. Well, we are going to write the same thing here, and I want you to know that S sub n represents the sum of the first n terms. Okay, so we're going to look at this formula down here as our means to our end here, but just know this. This is something you want to highlight, okay, because it's one of our formulas that we have to know how to use and remember. But just know that I'm going to give this one to you and do less of a kind of a formal explanation of why it works the way it does. So the rule for the sum of the first n terms, or S sub n, of a geometric sequence is as follows. We say the sum of the first n terms is A1. So what do we know about A1? Well, that's the value of our first term, okay, times, now in this quantity here we have 1 minus r to the n over 1 minus r, where r is our common ratio. So we have 1 minus our common ratio on top and bottom. It's just that on top here we also, on our common ratio, have an exponent that represents n, where n is the number of terms in our sum. So what we're going to do really quickly here is make sure that I know that you know we have a needs list. It means that we're going to need the value of our first term here. It also means that we're going to need to know the value of r, and it also means we're going to need to know the value of n. These are the three things we are going to need to know here in order to find the sum of the first n terms of a geometric sequence. So in other words, find a geometric series. So looking at these series that you see down here, or at least these sequences, it says on letter A here, please find the sum of the first 10 terms of the geometric series. And so you'll notice that this is definitely geometric. I can already see that this is doubling every time here. And so something that's worth writing, I'm going to take a moment, and I think you should too. So times 2 times 2 times 2 times 2 is our common ratio. As a matter of fact, I'm going to write down our common ratio 2 here. Now, with respect to what I want to find, I'm going to go ahead and write this out over here. I want to find the sum of the first 10 terms. So again, we're going to use this formula written right here, but I need the values of some things here. And so one of these things, r, is one we've kind of already discerned. How about the value of our first term? So now we actually do know the value of the first term is also 2. And then in terms of n, what is n? Well, in this case, n is 10. Okay, so we're going to write 10 because I want to add together the first 10 terms. If this is the case, and these are these three values on our grocery list here, well then we're just going to go ahead and put this together, and it always is kind of set up this way. So the value of our first term here, so our A1 was 2. We're taking this times in parentheses, so we have this big fraction here, and on top and bottom, no matter what, we have 1 minus now r. Now, the top and the bottom has this r, and in this case, our r value was easy to be seen. It was 2. We can see that over here in our sequence. But then this 2 on the top here has an exponent, and that exponent right there has to be our n value, where in this case our n value is 10. So I'm going to put a 10 here. Cleaning this up a little bit, really it looks like 2 times 1 minus 2 to the 10th over 1 minus 2. And with respect to what we're able to actually do here, this is kind of one of the first places we always stop. Let's go ahead and simplify our denominator. Now the top, one thing I can tell you about the top is 2 to the 10th is it's not huge. It's a getting bigger number. But the fact is it's going to be bigger than you probably like to try to figure out on your own. So at this point we're going to grab a calculator, and what I'd like to look for is the value of this inner stuff here. I'm going to make sure we make a note here. Find the inner value first. Okay, so with respect to our inner value, how am I going to put this on my calculator? Well, I tell you, the way you might write it is, in parentheses, we have 1 minus 2 to the power of 10. Now, you don't have to put around the 2 any parentheses here, just because it knows it's going to do the 2 to the 10th first before it subtracts it from 1. And then this is divided by, and this was all over 1 minus 2. Now, minus. In this case, we didn't get a decimal, and in some cases you may. But what I notice is that this inner part here is 1023. So what we end up with is 2 times inner part, which is 1023, which in this case I think is easy enough to do without actually having to pull out a calculator here, 2046. So this would be our sum of the first n terms. And you might say, well, that's kind of big, and I might come back with, well, you did take 2 to the 10th power, and you know, I suppose that would have the ability to make numbers rather large. Consider this also, if we're adding the first 10 terms of this sequence up here, then you're getting something that is doubling every time, and so getting rather large fairly quickly. Imagine if you had added up the first 25 terms of this, and it continues to double from term to term, it's going to grow rather large. So we're going to try again here on letter B to find the sum, but this time of the first 25 terms of a geometric series. And this time I want you to notice that our R value is half. That is to say that if you're talking exponential things, if your base of your exponent is less than 1, you're taking something times a half repeatedly, it's getting smaller and smaller. So we may not get a very, very large sum here, but let's go ahead and start with some basic things here. So first things first, let's write down, we want to find the sum of the first 25 terms here. Now in terms of our needs list, we need 3 things here. We need R, which we've been furnished with here, we have. We need the value of our first term, which we've actually been given as 1,000. And then we need our value of n, which in this case is 25. Now I'm really, really keen on going to set this up here. But one thing that I want to make sure we do is make reasonable sense out of this. So maybe we write out a first few terms here. We started at 1,000. If I'm taking this times a half each time, then I'm going to be at 500 next. Next up, I'm going to be at 250, and the next up I'd be at 125. Always good to look at kind of what's going on here. So we plan on adding up the first 25 terms of this series. You can already see that if we added up, just the first 4, we'd almost be at 2,000. So, something that it may not be super large, but it's also not going to be small here. Let's take a look at putting this together. So the sum of the first 25 terms, using our formula for the sum of a geometric series, says start with the value of your first term. So we have our value of our first term, which is 1,000. And we're going to take this times a fraction. Now we have 1 minus r on both the top and the bottom, and this r appears to the value of n. So our r value is a half. And up here we have 25 as our power. So this is going to get pretty ugly here with respect to a decimal. So on the inside here, what could I do first? Well, I'm also keen on doing 1 minus a half first, which is 2 halves minus 1 half, which is a half. So I can put a half down here. But what do we get on top? 1 minus 1 half to the 25th. So let's go ahead and tie this together on a calculator. I suppose that we get, again like last time, in parentheses, 1 minus, now this time I am going to put a half in parentheses because I need to raise all of that half to the 25th and put it in parentheses. So here's my numerator, 1 minus a half to the 25th, divided by, in parentheses, 1 minus 1 divided by 2. And in parentheses there. So in this case, suppose we get 1.99999994 is the value of this inner stuff here. You know what? Let's just do this. Let's do this. I wonder if we took 1 minus 1 half to the 25. I think that it'll be kind of like a repeating decimal like we see here. Well, for what it's worth, I suppose let's go ahead and take a look at what happens when we multiply this number here, 1.999999. So 7 nines and a 4. We're going to take 1,000 times 1.9999994-ish. If we take that times 1,000, you're going to get 1, 2, 3 here. We get about 1999.9994. So getting really close to 2,000 here. One thing I will say about the sum of finite geometric series, they're actually not the funnest sums to find, just because you will need a calculator to do it, and often you do run into decimals like the ones you see that we got here. So the last video, we're going to take a look at sums of infinite geometric series. Cheers.